Section 2.5 is on page 58, talks about autonomous equations and population dynamics. So, a first-order autonomous equation is an equation of the form x prime equal f of x or y prime equal f of t, where y is a function of t or x is a function of t. Phase line, something that's very important to us. You're going to be using that in certain labs to really predict the outcome of an experiment. dy dt, we set that equal to f of y. We say, well, if dy dt, if the derivative is positive, f is increasing. If the derivative is negative, the function is decreasing. And if the derivative equals 0, which in calculus were critical points, then the function is constant, right? And it's called an equilibrium solution. So, few things to find. So this is really going back to what we did in chapter 1, but now we're doing it on a bit more challenging problems. Remember there were only one equilibrium point. Here we have 3 or 4 or multiples. So let's look at problem number 2 on page 67. It says 1 through 4 involve equations of the form dy dt equal f of y, and here it is, dy dt equal some function of y. In each problem, sketch two graphs. First one, you get a graph f of y versus y, which is the solution. Determine the critical or equilibrium points. Those are called critical numbers in calculus. Classify each as asymptotically stable or unstable. Draw a phase line and sketch several curves of the solution in the ty plane. Test the second graph. Let's focus on the first graph. So first, initially what I do, I want to figure out the equilibrium. Well, if I set this equal to 0, I will get y to equal, and let's see what we have. Y equals 0, y equal 1, and y equal 2. Well, let's see how that works. If I go on this line, and if I sketch this graph, this is a polynomial. It crosses at 0, this is y, and this is f of y, or simply dy dt. 1 and 2. Now I know how to graph this. This is behaving like y cubed, and it's positive, so the endpoints look like that. The multiplicity on each of those is a 1. That's something that you learned in college algebra or pre-calculus. So if it's a 1, it crosses, and it looks like a straight line. So something like that. Well, let's see how this works. If I look at this derivative being negative, so it's negative to the left of 0, that means the function is decreasing. If it's positive, the function is increasing. If it's negative, the function is decreasing. And if it's positive, the function is increasing. Of course, you could make a chart if you want and pick test points, but it's a lot easier just to go by derivative is positive, you go up, derivative is negative, you come down. That's y, right? And now, excuse me, this right here is my phase line. That tells me almost everything that I need. This is my phase line, right? And I figure from it where things are going up or down. And let's see when I put a solution, and now I'm going for the second graph. Sketch several graphs of the solution. If I look at the solution to this differential equation without integrating, if I integrate, I need to use partial fractions, right? Because I'll be looking at dy divided by y into y minus 1 into y minus 2 equal dt. And if I integrate, then I have to use partial fractions. I'm going to find the solution and graph it without actually doing any calculus, just by simply using the phase line. Well, let's see. Y equals 0. I know y equals 0 is right there. Y equal 1. Y equal 1 is right there. And y equal 2 is right there. And let's see what I get out of this line. Below 0. Below 0, it's anywhere down here. The function is decreasing. So something like this. Do you see between 0 and 1 that it's going up? Between 0 and 1, it's going up. it's being attracted to y equal 1. Above, do you see it's decreasing? So anywhere between 1 and 2, between 1 and 2, it's decreasing and leveling off next to y equal 1. So 1 is absorbing on both ends, 0 is repelling on both ends. And what happened above? If I go above 2, do you see that it's increasing? Well, let's see. If I look at 0, 0 is repelling. We call that asymptotically unstable. And do you see y equal 1 is attracting on both sides? We say that's asymptotically stable. And y equal 2, it's repelling on both ends. That's asymptotically unstable. All right, let's do another one. Same directions. So it all has to do with the initial graph of the function. And that's why graphing is very important. I'm solving a differential equation without integrating. I'm graphing the solutions. So let's go again and let's call that dy dt. And this is y. Well, I know what this is. This is exponential decay, shifted down 1 unit. So instead of y equals 0, e to the negative x is a graph that looks like this. Well, let's see. If I pick to the left, the derivative is positive. That means the function y is increasing. And since here it's negative, the function is decreasing. And the phase line again is right there. That is my phase line. And here, I know that if I set this equal to 0, I'll get e to the negative y equal to 1, negative y equal natural log of 1, which is 0, so y equals 0 is the only point I have to worry about. That's the only equilibrium point. And if I get down to this, and I plot y equals 0, well, y equals 0 is right there. That's simple. This is a bit limited, but it doesn't matter really. Do you see that if you go from below 0, it's going to look something like this? And if I go above 0, do you see that that's going to be looking something like this? So do you see this is attracting on both ends? That would mean this is an asymptotically stable solution. Of course, y equals 0 is the equilibrium. That's where things are steady. And we're going to do the same type of problems, but now they're going to just make it a bit more realistic because we didn't have attract and repel. And that's where semi-stable comes in. It's the same as what we just did. That's what this whole section is about. So let's do this again. dy dt is given. Sketch a graph of f of y. That's f of y, and that's y, and let me line that up properly. Right there. And the same deal, if I set this equal to 0, that is a 0 right there. And this is y minus 1, y plus 1, so here we are. Just to show a bit more, let's say that's 1, and let's say that's negative 1. Well, I know this behaves like y equal, like y to the 4th, and since this has a multiplicity of 1, so this is y squared into y minus 1 into y plus 1. So this is a multiplicity 1, behaves like a line. This has multiplicity 2, it looks like a parabola. So there it is. And now, if I really go after the phase line, that will tell me everything that I need. And let's see what I need here. Positive, it's increasing. Negative, it's decreasing. Negative, it's decreasing. And positive is increasing. There it is. And this is my phase line. Again, very important. And I know my equilibrium is y equal 1, y equal 0, and y equal negative 1. So let me put those on the number line. Y equals 0 is right there. Y equal 1 is right there. And y equal negative 1 is right there. And then let me label those clearly. Y equal negative 1, y equals 0, and y equals 1. This is the actual solution, y as a function of time. Well, if I glance at this, okay, if I come from below, it's increasing. So something, let me use a different color here. Let's go with blue. It's increasing, so it looks something like this. And if I go between -1 and 0, it is decreasing, so something like this. Then decreasing again above, and it's increasing. So I notice y equal -1 attracts on both ends. That's called asymptotically stable. I notice y equals 0 attracts on one end and repel on the other end. That's the definition of semi-stable. And do you see that y equal 1 is repelling on both ends? That's unstable. There it is. A really fun section. I don't know, I think it is, but that's only me. And how about this problem? Well, this is y squared into 2 minus y into 2 plus y. So if I sketch a graph, and again, let me line this up properly. If I pick equilibrium, I have y equals 0, y equal -2, and y equal 2. Again, the phase line will give you everything. If you say this is dy dt, which is f of y, and this is y equals 0, y equal 2, and y equal a -2. Well, this is going to behave like -y to the fourth, so I know from graphing polynomials, it's going to behave like this. Multiplicity is 1, it crosses. Around 0, it's going to look like a parabola. Well, this is how parabola look like, and that's multiplicity 1. There it is. Or I got it backwards, but it's the same. So the phase line again is right there, and if I pick to the left, right here, derivative is negative, positive, positive, and negative. And there it is. Again, this tells you, look at that. This is repelling, this is asymptotically unstable. Repelling on one end, attracting on the other end, semi-stable, attracting on both ends, stable. Not every problem has those three, it just happened that those examples do. And let's see how this works. So if I sketch y equals 0, there's y equals 0. Let me line this up. There. So this right here is, I need, well, okay, I could label it anyway I want. I'm going to say this is y and this is t. This is the solution. So let's say this is 1, this is 2, and this is -1, -2. Again, you could scale it any way you want. As long as you label it, you're okay. So I have y equal -2, y equals 0, and y equal 2. Well, what do I notice? I notice if I move beneath, increasing, so it's going to level off next to 0, and this is going to push up, but it has an upper bound, and this is going to be coming down. So again, -2 is repelling on both ends, that's unstable. Y equal 1 is attracting on one end, repelling on the other end, that's semi-stable. And attracting on both ends, that's stable. And that's pretty much it. That's all you're going to have to do. Your homework is 1 through 9 odd, and number 5, do part A only.